Hello. In this video, we'll talk about electrical circuits modeling in the frequency domain and transfer functions. Before we continue, remember to subscribe in our channel, like the video and active the notifications. It helps us keep growing in YouTube. Modeling a physical system requires understanding its operation. In electrical systems, mastering modeling principles helps predict behavior and performance, essential for problem solving and building a strong foundation in dynamic control systems. Understanding electrical circuits in the frequency domain involves applying the same basic circuit laws as in the time domain. However, the frequency variable R replaces the time variable T. The node and mesh laws are applied similarly, allowing us to construct the circuit's equation in the frequency domain. To obtain an equivalent circuit in the frequency domain, start by writing the time domain equation relating voltage and current. Next, apply the Laplace transform to convert it into an algebraic relationship in the frequency domain. Finally, construct a circuit model that satisfies this current-voltage relationship, following the passive sign convention throughout. In the frequency domain, transformed voltage is measured in volt-seconds and transformed current in ampere-seconds. The voltage-current relationship is expressed in volts per ampere. Impedances are measured in ohms, and admittances in Siemens. The fundamental laws of electrical circuits are Kirchhoff's laws for currents and voltages. Kirchhoff's current law, or the node law, states that the total current entering a node equals the total current leaving it, meaning the sum of incoming currents equals the sum of outgoing currents. Kirchhoff's voltage law, or loop law, states that the total sum of voltages around any closed loop in a circuit is zero. In other words, the sum of voltage drops equals the sum of voltage rises. A circuit's mathematical model can be derived by applying one or both of Kirchhoff's laws. An important aspect of analyzing electrical circuits in the frequency domain is the location of the poles of their transfer function. Poles are the complex values of the variables that make the denominator of the transfer function equal to zero. Mathematically, a general transfer function can be represented as h of s equals n of s over d of s, where h of s is the transfer function, n of s is the numerator polynomial with coefficients of the variable s, representing frequency, and d of s is the denominator polynomial with coefficients of s. The values of s that make d of s equal to zero are called the poles of the transfer function. Poles are the frequencies or complex values where the system becomes unstable or its response becomes infinite. They are crucial for determining the system's behavior and stability, influencing its frequency response, impulse response, and other characteristics. Resistor modeling. The modeling of a resistor is given in terms of the current and the voltage across the resistive element, as defined by Ohm's law. V of T is equal to R versus I of T. Since a resistor does not introduce time-dependent behavior, its Laplace transform of Ohm's law is V of S is equal to R versus I of T. Inductor modeling. The modeling of an inductor in the time domain is based on the relationship between the voltage across its terminals and the current passing through it. This relationship is described by the following equation, where L is the inductance V of T is equal to L versus derivative with respect to T of the current in the time. When moving to the frequency domain, include the initial current in the inductor at Te is equal to zero in the model. The inductor's stored energy must be represented as a source alongside the inductive element. Therefore, the equation becomes V of S is equal to L versus S versus I of S minus L versus I of zero. To account for the initial stored energy, the inductor can be modeled in three ways. 1. As a voltage source in series. 2. As a current source in parallel. 3. If the initial current is zero. Capacitor modeling. In the time domain, a capacitor is modeled based on the relationship between the voltage across its terminals and the current through it, given by the equation I of T is equal to capacitance versus derivative with respect to T of the voltage in the time. When transitioning to the frequency domain, the initial voltage across the capacitor, at T is equal to zero, must be considered as the capacitor stores energy in its electric field. This stored energy is represented as a source alongside the capacitive element. Therefore, the equation becomes I of S is equal to capacitance versus S versus voltage of S minus capacitance versus voltage of 0. To account for the initial stored energy, the capacitor can be modeled in three ways: as a voltage source in series, as a current source in parallel. If the initial current is 0, considering the modeling of individual elements that make up linear electrical circuits, we can move on to modeling complete circuits, composed of two or more of these elements connected in various ways. RC circuit. An RC circuit consists of a resistor R and a capacitor C connected in series or parallel. These components create delays or store energy in a circuit. When powered by a direct current DC voltage source, the circuit exhibits notable time-dependent behaviors. Capacitor charging. When the switch is first closed or the voltage source is applied, the uncharged capacitor allows strong current flow through the circuit. As the capacitor charges over time, the current gradually decreases as the charge builds up, opposing further current flow. Time constant. The time constant is a key property of an RC circuit, calculated as the product of the resistance and capacitance. It represents the time it takes for the capacitor to charge to about 63.2% of its final voltage. The formula is Vc of t is equal to Vs versus 1 minus Euler raised to the power of minus t over R versus C. A circuit with an inductor, L, is known as an RL circuit and exhibits characteristics different from those of an RC circuit. Below is an analysis of the basic behavior of an RL circuit powered by a direct current DC voltage source. When the switch is closed, the current starts low as the inductor resists sudden changes in current. This opposition, called inductive reactance XL, depends on the voltage source frequency and the inductor's inductance. Over time, the current in the RL circuit gradually increases as the inductor energizes. The rate of increase depends on the circuit's inductance, L, and resistance, R. Higher inductance slows the current growth. The current, I over time, T, follows this equation, where V is the voltage of the source, R is the resistance, and T is the time constant, which is calculated as L over R. After enough time, the current in the RL circuit reaches a steady state, with no significant variations. At this point, the current is determined by the source voltage and circuit resistance, as per Ohm's law. When the voltage source is short-circuited, the inductor discharges its energy, generating a high reverse voltage that opposes the current change. This voltage can damage other components if precautions aren't taken. Because current through an inductor cannot change instantly, only specific devices can be switched off under load. Opening inductive circuits with unsuitable devices can cause electrical arcing. RLC circuits are circuits that include all three passive components: resistor, inductor, and capacitor. A series RLC circuit can be observed in the figure. For the circuit in the figure, the transfer function, considering I of S over V of S, will be H of S is equal to 1 over L versus S squared plus R versus S plus 1 over C. In a DC steady state, once an RLC circuit stabilizes, it behaves like a circuit with just a resistor. The current follows Ohm's law, I is equal to V over R, where V is the voltage and R is the resistance. The inductor acts as a short circuit and the capacitor acts as an open circuit. After the transient period, the current in a series RLC circuit will tend to zero as the capacitor acts like an open circuit. AC steady state, alternating current. When the RLC circuit is powered by an alternating current, AC source, the behavior is more complex and depends on the frequency of the source. At low frequencies, the inductive reactance, XL of the inductor, dominates, offering significant resistance to current flow. This causes the current to lag behind the voltage, resulting in a positive phase shift. High frequencies. At high frequencies, the capacitive reactance XC of the capacitor dominates, meaning the capacitor offers greater resistance to the flow of current. This results in a negative phase shift between current and voltage, with the current leading the voltage. Resonance. Resonance is a phenomenon that occurs in RLC circuits when the frequency of the source matches the natural frequency of the circuit. At this point, the total impedance of the circuit is minimized, resulting in a maximum current. Resonance occurs when the inductive reactance and capacitive reactance are equal in magnitude but opposite in sign. When an RLC circuit experiences transients, like sudden changes in an AC source, it exhibits damped oscillations. These oscillations arise from the energy storage and released by the inductor and capacitor. The duration for these oscillations to die out depends on the circuit's time constant, which is a function of the resistance, inductance, and capacitance. The way to solve any circuit can be described in the following 6 steps. Impedances of passive elements. Replace resistors, inductors, and capacitors with their complex impedances, considering the frequency of the applied signal. Laplace transform. Convert all voltage and current sources, as well as any time variables, using the Laplace transform to facilitate analysis in the frequency domain. Transformed currents. Introduce transformed currents for each mesh of the circuit with their respective current directions. Kirchhoff's laws in the frequency domain. Write Kirchhoff's equations for each mesh of the circuit, considering the impedances of the passive elements and the transformed currents. Solving the equations. Solve the simultaneous equations obtained in the previous step to determine the currents and voltages in the circuit in the frequency domain. Transfer function. Based on the solutions found, form the transfer function that relates the input to the output of the circuit, allowing the analysis of its behavior at different frequencies. As previously mentioned, this circuit can be described with 2 equations. The equation for mesh 1 will be R1 versus I1 of S plus LS versus I1 of S minus LS versus I2 of S is equal to V of S. The equation for mesh 2 will be LS versus I2 of S plus R versus I2 of S plus 1 over C versus I2 of S minus LS versus I2 of S is equal to 0. We can use any methodology to solve this system of equations. However, since we are analyzing the transfer function, we will consider that the transfer function is the ratio I2 of S over V of S. H of S is equal to LCS squared over R1 plus R2 versus L versus C squared plus R1 R2 C plus L versus S plus R1. In this video, we've explained the basic of electrical circuits modeling. If you have any questions, type in the comment sections. See you in the next videos. Bye.